All right, in this example, we're going to look at a particular vector field. In this case, E equals 5z to the cubed, epsilon naught z hat in volts per meter. And what we're going to do is we're going to solve this two ways. And it's a sphere of radius 3 meters. So it's huge, but that makes the numbers easier, so we'll go with it. And what we're going to do is we're going to solve it twice to show a real demonstration of the divergence theorem. So if you recall, the divergence theorem is, if we're using Gauss's law as our guinea pig, the divergence theorem states that if you take the surface integral of a closed surface, that's the equivalent to taking the divergence of it, which in this case gives you the charge density, and doing a volume integral over that same region. And so we're going to first solve this particular problem one way, and then we're going to solve that same problem this other way, and you're going to see that we're going to get the same result. And that's kind of a way that we can, first of all, review Gauss's law in integral form, but also practice using the divergence and show the equivalence of the divergence theorem. So we're going to accomplish a lot of things just with this one example. So first of all, we have a sphere within that sphere, there's an electric field that looks like this. Let's start by using Gauss's law in integral form. So your goal is what's the charge? So what's the total charge? So let's start by doing the integral Gauss's law. So Gauss's law in integral form. The first step is we need to choose our coordinate system and find our ds. So in this case, since it is a sphere of radius 3 meters, the sphere is kind of a giveaway that we're going to use the spherical coordinate system. And our ds in this case is it's a sphere. So if you just visualize a sphere, our ds, the vector that is always perpendicular to the surface, is going to be r, and our ds is going to be a combination of the theta and the phi directions, right? So it's going to be d phi and d theta. It's going to be our ds, and it's going to be in the r direction. And remember, these are not unit lengths, so we got to remember to add in its partners that always go with it by multiplying it by the radius to make it a length segment. So in the case of d theta, you multiply it by r. In the case of d phi, you multiply it by r sine theta. All right, so let's combine this a little bit. You're going to get, it's going to be in the r direction, and you're going to have r squared sine theta d phi d theta. So the next step is then we calculate our electric flux density and set up the integral. In this case, the electric flux density will just be equal to epsilon naught E, which is going to be 5z cubed over epsilon naught, so these cancel, which is nice, z hat. And note that this is in Cartesian coordinates, so we need to convert to spherical. So there's two things that we need to convert. The first is this z, right? So from our table, we know that z is going to be r cosine theta. So you can also see that if you just kind of draw a little theta here, it's going to be r cosine theta. So we're going to substitute that in. And then in terms of this vector, we're going to take the dot product with ds, so we can deal with it when we get to that point. So let's plug this z in and set up our integral. So our integral is going to be equal to our closed surface integral of d dot ds is going to be equal to double integral. We're going to write in our z. We're going to substitute r cosine theta in here. So we're going to have 5 r cosine theta to the third. That's going to be our our d expression. And then also we have the z hat dot ds, so we have a z hat dot r hat. And then we have this stuff, right, our ds, which is going to be r squared sine theta d theta d phi. So now we just, and then our limits are, we want theta, it's a sphere, so we want theta to go from 0 to pi, and we want phi to go from 0 to 2 pi, to go all the way around. And now we just have to clean up. So in this case, let's just go here. We're going to have, if we expand all this out, 0 to 2 pi, 0 to pi, let's see, we're going to have 5. This is r to the third plus another r squared. So we're going to have 5 r cubed. We have lots of cosine thetas, so there's 3 here. Oh, I forgot, we also have to clear this out. So z dot r, if you go back to our chapter 1 skill when we're taking, where we have the table of the dot products of the different vectors, z dot r is conveniently equal to cosine theta. So over here we have r to the fifth. We have lots of cosine thetas. Let's see, so we have 3 here plus 1 here, so cosine theta to the fourth. And then we have our sine theta, d theta, d phi. So now we just have to integrate this mess. Right? So let's pull out all the things that we don't have to worry about. So 5 r to the fifth. In this case, this closed surface is a sphere of radius 3. That's the closed surface that we're integrating. So let's just plug the 3 in here. So we have r to the fifth. No phis. That's nice. So we'll just go 0 to 2 pi of d phi. And then we have to integrate our theta, where we have cosine to the fourth theta, sine theta, boo. So I think this will require some separate futzing around. So this is going to be 2 pi. That part's nice. This, we're going to have to do our U-Substitution approach. So let's let U is equal to cosine theta, then du is going to equal to minus sine theta d theta, and so that means that d theta is going to be equal to du divided by minus sine theta. And we're going from theta equals 0 to theta equals pi, so when theta equals 0, u is going to be equal to, plug 0 in here, u is equal to 1. When theta equals to pi, u is going to be equal to, plug pi in there, minus 1. Let's plug all this in and clean it up. So we're going to have 2 pi times 5 times 3 to the fifth. Let's leave that 5 out for now. I have a feeling that that might come in handy. The 2 pi is from here, and then we have the integral from 0 to pi, so 1 to minus 1 of u to the fourth sine theta, minus sine theta, let's put the minus sign there, times sine theta du. And so then when we take this integral, you're going to have a factor of 1/5. So 2 pi, 5, 3 to the fifth, 1/5. Looks like I intentionally designed it that way. U to the fifth. And we evaluate that, or from, let's just swap the limits. So we have, or let's just keep this here, that's fine. And you evaluate that from 1 to minus 1. And so that's going to be, give you 2 pi, 3 to the fifth. Then if we open this up, you're going to have minus 1 to the fifth, minus 1 to the fifth. That's going to give you 2. Oh, oops, this should be just a plus 1 in here, but that negative sign distributes, so this is a plus. Point is, you're going to get 2 on the other end, and that is going to give you a grand total of 972 pi. And so in the end, we'll just write this out here. Your total charge is going to be equal to 972 pi coulombs. And so now let's try to redo the problem by doing the right-hand side of this equation. So I know that's going to make this a little longer than the usual video, but hang in there with me while we still have this fresh in our mind. Let's just do it the other way. So let me clear up some space. All right, so now we're going to kind of do the right-hand side of this equation. So to start out with, let's get the divergence of D, which is going to be the divergence of epsilon E. In this case, right now the Cartesian coordinates kind of work to our advantage because the divergence is a lot easier to do in Cartesian coordinates. So let's just keep it that way. So we have 5z to the third epsilon naught. The epsilon naughts cancel. Z hat, which is going to be d by dz of 5z to the third, which is going to be 15z squared. And remember, the divergence of D gives us the charge density that enables us to have the field that we're observing, or the electric flux density that we're observing. Now, since from our previous discussion, since this is a sphere of radius 3, we'll want to convert this to spherical coordinates. So in that case, we use the fact that z is equal to r cosine theta, and just plug that sucker in. So you're going to get rho v is going to be equal to 15 r squared cosine theta squared. And now to find the total Q, we just do the volume integral over that same region, right? So we're going to do triple integrals. Volume integral is actually, nicer because you just integrate over all the variables. You don't have to try to figure out what your ds is. So it's almost worth the cost of doing a divergence, right? So we're going to have, let's just write down our rho v, and then our dv for spherical coordinates. Once you lump them all together, it's going to be r squared sine theta dr d theta d phi. So just in the end, you'll probably just have this measure memorized as the dv for spherical coordinates, right? So you have your dr, your d theta gives you an extra r, and your d phi comes with an r sine theta. So together you get r squared sine theta dr d theta d phi, and you're integrating from 0 to 3. Theta goes from 0 to pi, and phi goes from 0 to 2 pi to get the whole volume of the sphere. So now we separate everything out. We're going to get 0 to 2 pi of d phi. There's no phi in this case, so it's just with a d phi. That's nice. That's going to give us 2 pi. And then we're going to have our theta, which is where we go from 0 to pi. It's going to be cosine squared sine theta d theta. I say, but now this is the same trick that we had for cosine 4 works, right? So we're going to say u is equal to cosine theta, skip a step, du over minus sine theta is going to be equal to d theta. So we're going to substitute that in, and then when theta is equal to 0, u is going to be equal to 1. When theta is equal to pi, u is going to be equal to minus 1. Same drill, right? And then over here, in terms of r, we're going to have, going from 0 to 3, of 15 r to the 4th dr. So now continuing on, 2 pi, this is going to be integral from, let's see, you're going from 1 to minus 1 of minus u squared, and then the sine theta is canceled. The negative came from this negative sine theta that we had over here, so it's just like what we had before, du. And then we can just go ahead and do the integral for this. So the integral of r to the 4th is 1/5 r to the 5th. So we're going to have 3 times r to the 5th evaluated from 0 to 3. And so that is going to give us 2 pi. So taking this integral, we're going to have the u squared integral is going to be 1/3 u cubed. So we're going to have 1/3 and then minus u cubed integrated from 1 to -1. So if we expand that out, that's going to be minus -1 cubed plus 1 cubed. So that's going to be equal to 2. And then over here you have 3 times 3 to the 5th. So this total thing is equal to 2, so this integral is going to be equal to 2/3 effectively. So you have 2 pi, 2/3, and then 3 times 3 to the 5th is going to be equal to 729. And if you punch all that into your glorious calculator, you're going to find that Q is going to be equal to 972 pi coulombs, which is the same as what we saw over here. So you will find that the divergence theorem works. So in summary, we kind of solve, we have an electric field, which is in the z direction described by this function that we're only concerned about the volume of a sphere of radius 3 meters. And we use that to find to prove the divergence theorem or show the divergence theorem, right? We did some Gauss's law in integral form practice by taking the surface integral of this. That involved converting the z to spherical coordinates, but then also finding our ds. In taking the dot product process, we also had to find z dot r and substitute that in, did the surface integral, came up with our conclusion. But we also came up with the same result by using the right-hand side of the divergence theorem, which is where you take the divergence, which gives you the volume charge density, and you do a volume integral over that same volume, and then end up with the same result. So the key take-homes is be able to set up and execute the surface integral, be able to take the divergence, be able to take a volume integral, and know how to use both of these approaches to solve this particular problem. And then usually you can then decide which one ends up being easier.